Good morning, good afternoon, good evening, and good night, depending on where you are. This is the second day of the first session. I hope everything will run so smoothly as yesterday. Today we have many talks on alpha clustering, on clustering in general, and there is also a talk on interesting physics that happens at and beyond the proton dripline. So maybe we can start with the first talk, will be given by Soichi Ishigawa-san. He would talk on 3 alpha continuum states and the triple alpha reaction. Soichi-san, please.
Yes. Can you see my slide?
Yes, we can.
Okay. So, hello everyone. I'm Soichi Ishikawa from Hosei University in Tokyo. So first of all, I would like to thank the organizer for giving me a chance to talk in this workshop. And my talk will be something related to 3 alpha models as a carbon-12 nucleus. And in particular, I will show you some calculations about photo industry. Let me show you. Okay, photo-induced 3 alpha breakup of carbon, calculated in terms of 3 alpha particle models. And this is an inverse process of the so-called triple alpha reaction, which is a key step to produce heavy elements in stars. And once we have cross-section for this disintegration process, we can calculate triple alpha reaction rate in this formulas. Okay. Then this is some energy levels of carbon-12. We have 3 alpha breaks up threshold here. And below 3 alpha thresholds, we have 2 bound states, which is called ground state of carbon-12 and first excited state of carbon-12, which has a 2+ state, angular momentum state. And just above the 3 alpha threshold, we have very sharp resonance, which is a 0+ state. This is called so-called Hoyle state. And above the Hoyle state, we have some resonances confirmed. One is 3- states and 1- states. And around here, there are some experimental report shows that there are some resonances for 0+ or 2+ state. Experimental result for the resonance energy is a little bit different dependent on reaction mechanisms. But anyway, maybe about 2.5 MeV, just about 3 alpha threshold energy. We have 2.5 energies, MeVs above the 3 alpha breakup threshold. Okay, so I should calculate all these process in the 3 alpha models. So by 3 alpha models, I have 2 essential input. One is just the 2 alpha potential. This can be constructed from scattering data of alpha-alpha elastic scatterings. And another input for the model is 3 alpha potential, which depend on coordinate of 3 particles. That's at least I don't know how to microscopically construct this potential. So I just use determine the I assume the form of 3 alpha potentials phenomenologically. So just I want to show some model dependence of the following result. And in the following, I will just mention some models and interaction models, and then show some results for this integration cross-section, as well as the alpha reaction rate calculated from these cross-sections. Okay. Yes. So model is model is very simple. Just alpha particles is considered as a structureless boson, just a point in the structure. It's just ignored, and we use 3 alpha Hamiltonians as well as photon operator, because I will calculate photon disintegration process. And for that, I will define the wave functions for the breakup process, like this ground state, bound state wave function multiplied by photon operators. And then this is a 3-body green functions, which particles in which particles 3 alpha particles are going away. So by these definitions, we can say this wave function is a 3-body photodisintegration wave functions for the 3-body photodisintegration process. And then we solve these wave equations using a 3-body Faraday method. I will not talk about calculation method in this talk, because there is no time for that. I just say I use Faraday equations to solve 3-body program. Anyway, once we have this wave function, from this wave function, I can calculate transition amplitude from bound state to scattering state. This Q and P is a relative momentum alpha, and also spectral momentum relative to central mass of 2 alpha systems. These are 3-body wave functions. This is transition amplitude. And from this transition amplitude, I can calculate cross-section for the photodisintegration process. Okay. This is some technical terms. Okay. From to construct 3 alpha Hamiltonians, we should introduce some interaction models. As I said before, I used 2 kind of first 2-body potentials, 2 alpha potentials. This is we have some traditional or conventional potential in hand, which is called Arrhenius potential. This potential have some simple Gaussian form with some attraction as well as short-range repulsion, which represent the Paris principle between alpha particles. Okay, so parameters is like this, and this shows this figure shows scattering phases of alpha systems as energy functions energies. So this potential is constructed to fit this phase shift for angular momentum 0 state and 2 state and also 4 state. Okay. So
excuse me.
Okay. And yeah, this is the standard potential model for the alpha-alpha systems. And in addition, yes, to two-body potential, I should introduce three alpha potential, which depend on three alpha coordinate of three alpha particle system consistency. Because if calculate binding energy or resonance state only two-body potential, one cannot reproduce such observables, right? Okay, and yes, and since as I mentioned before, there is no practical theory to construct the three-body potential in this hand. At least I don't know. So I should choose a phenomenological way. I just assumed Gaussian form with some with range parameter A, and for each partial waves, each angular momentum state, I should input define strength parameters for potential. So I choose four values, four values for range parameter A, like this. And each parameter, I determine the strength of three-body potential in this way. For 0 plus state, strength parameters is determined to reproduce Hoyle state energies. And also 1 minus and 3 minus state, strength parameters are determined to these resonance energies. The whole 2 plus state, we have bound state. So for 2 plus state, strength parameters is determined to reproduce this binding energy of carbon 12. Okay, so the resulting parameter is something like this. So anyway, I have at least 4 different models which correspond to 4 different parameters of 3 alpha potentials, range parameters for 3 alpha potentials. Okay, so I show in the end I show some result for integration process. Second, 2 plus excited state of carbon to 0 plus state, which includes Hoyle state. And second one is ground state to 2 plus state by E2 photon. And third one is 0 plus state to 3 minus state. I also calculate 0 plus state to 1 minus channel, but this is very small, so I'm not sure this for state. Okay, so this is the result of the photo-dish integration cross sections for each reactions. So this one is carbon excited state to 0 plus state. As a function of energy, which measured from 3-body alpha, 3 breakup threshold. And this is 0 plus, this is very sharp Hoyle state energies. And some model dependence appears here. And here, each curves I designate model dependence by color of lines. Model 1, black, and model 4, blue, and something like this. And for 0 plus to second 2 plus state, result is here. So there is rather large model dependence. And for this reaction, we have some experimental data from for the photo-disintegration cross section, just I plotted here. So in this case, model 3 or model 4 are consistent with this experimental data. And for 3- state, there is very sharp resonance because the resonance energy fit to strength parameter is fitted to reproduce resonance energy. So these models have a same energy of resonances, but slightly different gamma decay widths. Okay, from these cross sections, disintegration cross sections, I calculate triple alpha reaction rate as a function of temperatures. T7 is a temperature of in terms of 10 to 7 Kelvin. And for lower temperatures, this is model 1 to model 4, depending on colors. And each, at the low temperatures, model dependence are rather mild, but as temperatures increases, quite different quite large model dependence appears. And for model 2, red line in this, I brought some contents of the final state. 0 plus contribution comes from right here. And it found that this comes from, essentially comes from, mainly comes from Hoyle state. And second contribution from second plus state arises as temperature arises. And 3- contribution from 3- states are rather small. And this is 0 plus contribution for the reaction rate. And yeah, the models dependence are rather mild, not so much dependent. But this comes only from, mainly comes from Hoyle state. But for 2+ states, ground state to 2+ state transition, there are large model dependence. So model dependence of this total reaction rate mainly comes from ground state to 2+ state transition. Okay, so this is my summaries. Yeah, I calculate photo disintegration cross sections or each channel, each transition channels, from which reaction the rate is calculated. And contribution from 0 plus states dominate at lower temperatures. But as temperatures increases, contribution comes from 2+ states are very large. And also there are much of large model dependence appears. Okay, that's all. Thank you very much for attention.
Thank you very much for this interesting talk. Now we have a time for 1 or 2 shorter questions. Longer question, please keep for the discussion session. Wait a moment, I do not. I do not see.
Hans has got his hand up.
Yeah.
Yes, Hans, yes, please.
Can you hear me?
Yes.
So I just wanted to hear whether you had tried to compare your reaction rate to other reaction rates on the market.
Yes, just let me back. Yeah, that is rather small, I would say, because width of the Hoyle state is calculated width of the Hoyle state is about 2/3 of the experimental values. So resulting reaction rate is essentially 2/3 of the other reaction rate, which, for example, nuclei or something like that.
Mm-hmm.
So this is another problem. But if width of Hoyle state is adjusted, almost same reaction rate is obtained.
Mm-hmm. Okay, thank you.
I don't see other questions, so let us thank the speaker, and we come to the next talk by Yunki Tanaka-san on probing surface alpha clustering in the ground state of stable heavy nuclei. Please, yes, we see your transparency.
Do you see my slide?
Yes, we do.
Okay. Thank you very much for your introduction. I am Junki Tanaka from Rike Nishina Center. I appreciate the organizer to give me this opportunity that I can introduce my our experimental result. This is the experiment for my during my postdoc in Darmstadt. Okay, so let me start from the introduction. Correlations and clustering are the universal phenomena in the composite system, ranges from the universe to the quarks. The atomic nuclei is a unique many-body quantum system which contains protons and neutrons, and this can be described in the mean field models. On top of this, correlations among nucleons play an important role in understanding the property of atomic nuclei. After the prediction of alpha clustering, microscopic theory have been developed, presuming the correlation of the nucleons in the clusters are strong, while the intercluster correlations are weak. For light nuclei, cluster structures are experimentally known to exist in their ground state, as well as in excited state, in particular for the state at the energy around the cluster emissions threshold. On the other hand, in heavy nuclei, a consistent description of nucleons in the mean field and alpha clusters in one model is challenging. For alpha decay nuclei, alpha clusters are essential ingredient. As explained by Georgi Gamow, the performed alpha particle penetrate the Coulomb barrier by the quantum tunneling effect. However, it is not clear whether this alpha clustering is the special phenomena only for the alpha decay nuclei, or it is general even in normal, like stable heavy nuclei. To answer this, we started our research program from the tin stable isotopes. Tin has a proton 50 shell closure, and the neutron side, there are no major shell gap. Recently, the alpha cluster formation in the surface of the heavy nuclei is described in generalized density functionals with explicit cluster degrees of freedom. In this theory, the binding energy of the alpha particle change in the nuclear matter depending on the baryon density. At zero density, it corresponds to the binding energy of bare alpha particles. By increasing the density, the binding energy decreases, and thus the cluster gets dissolved in the saturation density. Here, I am showing the alpha formation amplitude as a function of radius. It locates around the nuclear surface because the density decreases at the surface region, and the system gains the binding energy by forming alpha clusters. Solid line is 14112, and dotted line is 14124. The top is the same as one before, and the bottom is the isotopic dependence of number of alpha particles in the surface. X-axis is mass number. Here is tin 112, and here is for tin 124. It decreases smoothly when increasing the mass number. The number of alpha particles are almost double for tin 112 compared with tin 124. To explain this trend, I show you the proton and neutron density distributions for tin isotopes. These are for tin 116, 120, and 124. Red are protons and neutrons are blue. Because the alpha clusters get dissolved at the saturation density, we will only focus on the surface. According to the theory, alpha particles appear below 1/10 of the saturation density, which correspond to below 0.016 in density. Please compare 116 and 124 in this zoomed region. In case of 116, below this density, comparable number of protons and neutrons are there. While in 124, since neutron skin is developed, protons are much less than neutrons. Because of this unbalanced proton to neutron ratio, the probability to make alpha particle becomes less. Of course, it is because alpha particle need 2 protons and 2 neutrons. This effect leads this double difference. Then, experimentally, how can we demonstrate the alpha clustering on the surface? The convincing way is to show this isotopic dependence. The cross-section of the alpha knockout reaction is one observable, which directly reflects the isotopic dependence of the number of alpha particles on the nuclear surface. In this figure, the top is the initial state of the alpha knockout reaction, and bottom is the final state. A proton beam is incident on the tin target, and alpha particles on the surface are knocked out. Since both proton and alpha particles are emitted in the final state, and then we can obtain the missing mass spectrum of the cadmium residue. The experiment was performed at the Ring Cyclotron Facility Research Center for Nuclear Physics in Osaka University. This figure is the experimental setup. Protons beam accelerated up to 392 MeV was incident on the tin target. The momentum of the protons and alpha particles were analyzed by using a ground Leiden spectrometer and large acceptance spectrometer, respectively. And we constructed the missing mass. This is the result of the experiment. The missing mass for tin 112, 116, 120, and 124 pp alpha. X-axis is missing mass. We observed the strong transition from the ground state of the tin to the ground state of the cadmium. The higher part are the transition to the excited state of the cadmium. To see the trend of isotopic dependence, these peaks are integrated, and the result is shown in this panel. We observed the smooth decrease of cross-section by increasing mass number. So next, we would like to compare this result with the theoretical prediction. To do this, we used the reaction theory and converted the predicted number of alpha particles to the pp alpha cross-section. So we used the distorted wave impulse approximation. This is often used for quasi-elastic scattering, such as P2P reactions. The reaction analysis can be summarized into 5 points. The first point is that we properly take the reaction kinematics into consideration. We collectively treat the slight differences coming from the target mass or Q value difference in different isotope. The second point is we use the P alpha scattering matrix for free space P alpha matrix as an interaction. And third point is we use the momentum distribution of the initial alpha particle in tin nuclei. And for this, we use the theoretical prediction based on the generalized density functionals. We also take the absorption of protons and alpha particles into consideration using the global optical potentials. And I need to mention here that only the imaginary part of the optical potential for emitted alpha particle and cadmium system was normalized to fit the experimental data. And the same reduction factor was used for all the isotopes, not to change the isotopic trend. Then I overwrote the result of the result of the reaction theory analysis on the experiment. The red square is the theoretical calculations, and it shows good agreement with experimental result. The arrow here is an interpretation based on the theory that for tin 112 with thin neutron skin has more alpha particles, and for tin 124 with a thick neutron skin has less alpha particles. So this is the summary up to here. First, the existence of alpha clusters in the ground state of heavy nuclei was clarified by measuring the cross-section of the alpha knockout reaction. The isotope dependence of the reaction cross-section is consistent with the theoretical prediction and is likely to be an alpha particle localized in the on the nuclear surface. And based on the experimental result, it is considered that the ground state of the tin nucleus is not always such a one body, but alpha particles are repeating generation and annihilation in the nuclear surface. Okay, so our experimental result was published in Science report. In the report, we further mentioned that the relation of nuclear eos and also the origin of alpha particle in alpha decay. So I would like to briefly introduce our further plan related to them. According to the density functional theory, not only the formation of alpha clustering depending on the neutron skin thickness, in the opposite direction, neutron skin thickness is affected by the formation of alpha clusters. This was originally calculated in tin isotopes, but the same things is expected for lead isotopes. These figures are the formation of alpha clusters in lead isotopes, lead-204 to lead-208. This is the formation amplitude for 204 to 208. For the moment, one of the way to extract the slope parameter in nuclear eos from the experimental information is to use this relation between neutron skin thickness and slope parameter. And the existence of the alpha cluster may change this relation. Alpha existence of alpha cluster may change the neutron skin thickness. I'm showing here, for example, for the tin isotopes. For example, tin 120, this black is with alpha correlation, and this open circle is without alpha correlation. If we take the alpha correlation into consideration, then neutron skin thickness changes like this. So formation of alpha cluster will change the neutron skin thickness, and which will change the relation between neutron skin thickness and slope parameter. And then finally, it will also affect the determination of the slope parameter. This is the calculation for the lead isotopes. So neutron skin thickness and slope parameter, and this blue is for without alpha correlation, and red is with alpha correlation. If we properly take the alpha clustering into consideration, then from the same measured neutron skin thickness, L parameter determination will change. So for this purpose, we would like to observe the alpha clustering in lead isotopes. And the next is alpha decay related. I'm showing the polonium and thorium isotopes here. And these are the short-lived alpha decay nuclei. Alpha decay study shows the isotopic dependence of reduced alpha decay width, which is considered to be the surface alpha formation amplitude. We would like to perform the alpha knockout reaction on these nuclei and confirm so-called preformed alpha particles are really preformed. In the left figure, it illustrates a good aspect of the PP alpha reaction, that the PP alpha reaction can give the kinetic energy to the preformed alpha particles to get out of the Coulomb barrier easily, which shows the contrast to the alpha decay, where the half-life is so sensitive to the barrier penetration. These photos are the facilities in Riken, Nishina Center, cyclotron, and separator to produce these polonium and thorium beams, and separator, which we plan to use for spectroscopy station. We further plan to probe other clusters like helium-3 and triton in the nuclear surface. For example, this is the formation amplitude of triton and formation amplitude of helium-3, depending on the neutron fraction. The formations are different depending on the triton and helium-3. This is half and half for proton to neutron ratio. And if neutron increase, of course, triton, not of course, but triton increase, but helium-3 decrease. We would like to observe this change by changing the isotope, like isotopic. We would like to observe this kind of effect in isotopic trend in PP alpha cross section. So I rushed too much to explain our future plans. So if you are interested in this kind of project, please contact us. So this is all, and thank you very much for your attention.
Thank you very much for this interesting talk. Now we have the time for a few questions. There are several hands up. Maybe Olivier Sorlin would start.
Diego was the first, but okay, I can start. Thank you very much. It was really great, great presentation and a very beautiful result. My question is that did you do also PPN and P2P reaction together with PP alpha to know which fraction of alpha you have at the surface as compared to the protons and neutrons?
We did not do that, P2P or PPN. We just selected the angle for PP alpha channel. So the answer is no.
Would that be possible or interesting just to have an idea of which fraction is it as compared to kind of, if you compare PP alpha, PPN and P2P, you should see the same in the n equal close to n equals z, and then a change to neutron rich, and to see how it's correlated with your alpha preformation, so to say.
Yes, I think so. I think that is interesting to observe.
Okay, we have the time for one short question. Diego Guerra.
Yes, thank you. On your slide 15, you showed the correlation between the neutron skin and the L parameter with the RMF calculation.
Yes.
Yes, this one. So the new calculation by Stefan Tippel, it seems that the correlation is not linear, while in the original work it is. Do you know why this? And second, very short question, with this new finding, the measurement of the neutron skin of lead 208, if you take into account the alpha correlation, will lead to L values larger than what was extracted in the recent PRL. Is it true?
Sorry, do you hear me?
Yes, we hear you.
Okay. For the first question, the reason why this, I do not exact reason, but at least these calculations are based on relativistic mean field calculation and non-relativistic Hartree-Fock calculation. And this Stefan's calculation is rather simple relativistic Thomas-Felmy calculation. And those two, that is the difference between this and this. And I did not catch the point of the second question. Can you briefly?
Well, maybe we keep this question for the discussion session. We are running out of time. So thank you very much. And
as was said by Guillaume, you can raise your question on the chat, and so that that can be taken for the discussion.
Exactly. So thank you very much, Tanaka-san, and